This is our second lesson for our waves unit for Physics 11, and in this lesson we're going to take a look at something called refraction. Now, just a quick little reminder of where we left off last day. Last day we were looking at reflections, and we talked about how for a mirror it was actually really nice. The angle on the way into the mirror is equal to the angle on the way out, and in the world of physics we love measuring compared to this normal line. Well, with refraction we're going to see that light beams will actually do a bit of a bend when they go from one material to another. And one of the main reasons for this bend is because there's actually a speed change when light beams go from one material to another. Light does travel at the speed of light in a vacuum in everybody's reference frame, but in things other than a vacuum, light does actually slow down. So yeah, generically, maybe we can put this into our notes that refraction is just about the bending of light at a boundary between two different materials. But before we get into that bending, let's take a moment, and part one of this section of notes, let's take a look at the speed change. So yeah, it's true that light does travel slower in anything other than the vacuum of space. So in water it slows down, in glass it slows down, and different materials it has a different amount of slowing down. To calculate how much the speed does actually slow, we use this thing called the index of refraction, and it's denoted in physics by the lowercase letter n, and every material has its own value for n, for this index of refraction. And that number is nothing but the factor by which light slows down by. Here's a list of about 5 of them. There's a bigger list that's actually in your textbook pages, and these are not numbers that you memorize. You can just look them up whenever you need them. In the vacuum of space, the index of refraction is exactly 1. Light doesn't slow down in a vacuum, but in every other material it does. Now, worth noting, in air, it barely slows down. To 3 sig figs, which is where we usually play, it pretty much looks like 1. So we're going to use a value of 1 for the index of refraction for air because it just won't make any difference. But for water, I can see light slows down by a factor of 1.33. Take a look at diamond. Light slows down by a pretty large factor there. And so one calculation that you might be asked to do, and these are actually fairly easy calculations to do, would be to find the speed of light in any one of these materials. So if somebody asked you to find the speed of light in water, all we have to do is take the usual speed of light, 3 times 10 to the 8, and then divide by the index of refraction because we want to see a number that's slower. And so dividing by 1.33, I have this value now of 2.25 times 10 to the 8 meters per second for water. And it's because of that slowing that we're going to get changes in direction when light goes from one material to the next. So part 2 of the notes, let's take a look at the angles. My first scenario, I've got 2 different materials. On one side of the boundary, I've got water, and the slowdown number, just pulling it off the table, 1.33. And on the other side of the boundary between the 2 materials, let's put some glass. And the slowdown number for there is more significant. It's 1.50. And we're going to watch what happens to this beam of light as it goes from water, where light's a little bit slow, to glass, where it's a lot slower. Now there's a neat way to think about which way this light beam is actually going to bend. You can think about driving a car. And in this case, since I'm trying to go from faster water to slower glass, imagine you're driving your car just kind of casually down the road, maybe you're not paying attention for a second, and you go off the faster pavement into some slower sticky mud. And if you were just not being particularly attentive and just kind of let your car cruise off the road at a bit of an angle like that, when it gets to that boundary, that transition, the passenger side tires are going to hit this slower sticky mud first. And that's going to cause the car to do a bit of a twist as the passenger side slows down. Once the car is fully in the mud, then it will actually travel straight again. But by now it's already done a bit of a twist. And this is what refraction is all about. Now in the world of physics, when we're trying to measure the angles in this story, we don't want to measure compared to the boundary. It works better to measure compared to this perpendicular line that we can add in, called the normal line. And so we'll measure the angle here on the fast side. That'll be our angle on the way in, the angle of incidence, and then we've got this refracted angle, this angle on the way out. So going back to our story, there's my angle on the way in. The glass is slower and sticky, so the light beam is going to bend towards the normal as it goes into the glass past that boundary. Now let's take a look and see if we can figure out how to calculate the angle over on the glass side. I'm going to call that theta r for angle of refraction. A lot of the times people like to just call this angle 1 and angle 2, and that's totally fine. To do these calculations, we're going to use something called Snell's law. So Snell is an old physicist who's no longer with us, and his equation is beautifully symmetric. Just looks like a butterfly, the exact same letters on both sides. And so in Snell's law, where I have n1 sine theta 1, this side, hey, maybe that could be the water side. And then I've got an identical calculation happening for the other side. In this case, the other side of my boundary is glass. And it's literally a case of plug and play. There are 4 values here, the n, the theta, the n, and then the theta. You'll know 3 of them, and we're looking for the 4th. So let's make an example up. Let's say that the angle on the way in is 40 degrees, and then it's going to hit that slower, sticky glass. Well, I can just drop the numbers in. I can grab the indices of refraction from just a data sheet from your textbook pages. 1.33 for water, sine of 40 degrees, and then 1.5 sine of the angle at the end of the story. When I asked my calculator to go 1.33 sine of 40, ended up with 0.85, and I still have this 1.5 multiplied onto the sine of the final answer. So I divided by 1.5 to clear that out of there, and I ended up with a decimal 0.57-ish is equal to the sine of the angle of refraction. All you have to do now is just invert the sign, so we'll use the second function button on our calculator, and we can see that that slightly smaller angle, it's not 40 degrees anymore, is 34.7, around 35 degrees. Now I'm just going to clear out all this calculation for a minute and just again show you how beautifully symmetric looking Snell's law is. So for our story here, Snell's law says, yeah, the n for the water, sine of the angle for the water. The n for the glass, the sine of the angle for the glass. It's just this beautifully simple little equation that works great. Now, if all I did was tell you that the light goes in and it all goes through and bends, I would be lying to you. I mean, that's the thing we're trying to look at today, but it doesn't entirely do that. A portion of the energy, a fraction of the energy, when it gets to this boundary, will actually reflect off much like a mirror. And so to be truthful, I probably should add in another little ray here. So I'm going to go and do that and just say that, yeah, you know what? A fraction, a portion of that light energy is actually reflected back. It would be at a 40-degree angle compared to the normal. And then a portion of it makes it into the glass. And I've just arbitrarily made them, the little rays blue and purple and green, you know, just for sake of clarity there. Not that the light would actually be that color. The idea that a fraction of the energy reflects off and a fraction transmits through this boundary is actually analogous to what we were looking at with slinkies last day, when we said if you had a thin slinky hitting a thicker one, a portion of the energy bounces back and a portion of the energy actually makes its way through. It's a completely analogous story. This is just for light beams. Now, I can actually simulate this story of a light beam trying to go from water to glass with this little refraction simulator. And so I can pick my materials. I'm going to go from water to glass, turn my laser beam on, and you can see that, yeah, it is true. A portion of it reflects off, just like a mirror, you know, maybe 40 degrees, 40 degrees. That looks like a little bigger than 40, maybe around there. And then a portion of the light gets through, but you can see there's a subtle little bend here. It's actually more noticeable if I make the angle bigger compared to the normal. I can definitely see there's some refraction happening there, and definitely reflection as well, right? And we can use Snell's law to find this angle of refraction, and then just equal angles for the reflection that's there. Okay, well, let's try this again. Slightly different scenario. Let's try having a light ray that goes from glass to air. So glass is quite slow, and then we're going to go to air, which is noticeably faster. And the angle on the way into the boundary, as we're traveling through glass trying to get to the air, is going to be 41, and we're going to try to find the angle afterwards. So the picture in your notes might look something like that. And thinking about this in terms of the cars, remember the glass is slow. It's like you're in the mud at the beginning trying to get back on the fast highway. So the picture would look like this. And as your car goes from the slow mud onto that fast pavement, those passenger side tires are going to grip first, and they're going to cause the car, when it gets to that boundary, to do a bit of a twist. And then it will track true after that. But there's definitely going to be some refraction, and we're going to find that the angle compared to the normal grows as you go into this faster material. And the math will take care of all of that for us. Okay, so there's my picture. Got my angle on the way in, my angle on the way out. I didn't draw the reflected ray. There would be a bit that is, but let's just look at the refraction portion. There goes Snell's law. I generally don't bother with I's and R's. I just like to think of it as side 1 and side 2. Putting in the values, 1.5 on the glass side for the index, sine of 41 degrees, and then 1 for air. Might as well use 1, it's so close to it. And I find that the left-hand side works out to a pretty big number. It's getting close to 1, 0.9844. And then when I unsign it, I end up with 79.8 degrees, almost 80 degrees. Let's just see if that looks right with the little simulator as we go from glass to air. So 41 on the way in and a pretty big 80-degree angle on the way out. So let's turn my laser off here for a second. 41, I don't know, around there. And we're going to go from glass to air. Okay, so we should see a pretty big air angle on the other side. Yep, yeah, it might be more like this. So 41 degrees, and then a really big angle here, like 80 degrees for that refracted ray. Oh, yep, some reflection as well, 41, 41. One of the things we're going to see, 2 examples down the road, is what happens if you try to make this angle too big. And if you're not careful, if I make it too big, look at what's happening to that refracted ray on the bottom. Eventually, it becomes 90 degrees, and it's got nowhere to go. And at that point, instead of having a split, a percentage of the energy go in and a percentage bounce off, all of it bounces off, and it just behaves like a mirror. And this is called total internal reflection. We usually just call it TIR, but we'll get to that a couple of examples down the road. Next one I want to look at is what happens if a beam of light is shone through a window pane. So you're in the air, then in the glass briefly, and then back into the air again. And you might draw that like this. So there's the pane of glass, and maybe somebody shining a blue laser beam through it. I'm going to make my measurements compared to the normal, and as it goes into that slow, sticky glass, it's going to twist towards the normal. So I'll talk about those first 2 angles as just being 1 and 2. Then it's going to get to the other side of the glass window, and it's going to do a little bending there. Maybe I'll call those angles 3 and 4. I'm going to just make up a number for the very first angle and just want to walk you through the calculations here. Let's just propose that the first angle here is 50, just making that number up. So 50 degrees on the way in. I could do a nice little Snell's law as I go from the air to the glass. And there's really nothing special about the colors here. I've just chosen blue, purple, green just for clarity. And I can do Snell's law to find out that the angle just inside the glass is around 31 degrees. Now I get lucky. There's a bit of a Z shape happening here, alternate interior angles they're officially called, and that means that angle 2 and angle 3 will be the same. So angle 3, because of that Z shape, is going to be 30.7 degrees, and now I can go from angle 3 to angle 4. Now, there's no real surprise with what's going to happen with the math, because this purple stuff is the exact same as this purple stuff. We're going to go right from the blue to the green and see the same numbers there, and you end up with a 50-degree angle again. And that's just because those 2 purple values were exactly the same. So that's if you go from air through glass to some air. And what you'll find is, in the end, the light beam is traveling the same direction. So that green arrow is traveling the same as the original one, but it's just jogged to the side a little bit. Less than the thickness of the window, actually, so not by very much. Next scenario, what if you were to go from, say, water? Maybe you've got a flashlight that's underwater and it's shining a beam of light, and it goes from water through the glass wall of an aquarium, out the other side into the air. So I'm going to mimic that like this. And so here's a light beam in the aquarium trying to make its way out. Well, I would do Snell's law again in order to figure out what the angle would be in the glass when it's temporarily traveling through the thin little pane of glass. Then it gets to the other side of the glass, and it's going to do refraction again. Now, I'm going to just propose an angle, making it up. and I say, hey, what if it was 40 degrees? So here goes Snell's law between water and glass. I run the numbers, 1.33 times the sine of 40, divide by the 1.5, and then unsign it. I get around 35 degrees. But just like before, that angle 2 is going to equal angle 3. And so we can go from angle 3 to angle 4 with Snell's law again. And I'm going to try to find that fourth angle. Now, just like with the window, this purple stuff here, mathematically, is the same as that purple stuff. They're exactly the same. So you could have just gone right from the blue numbers there that I have for the water, right to those green numbers that I have for the air, simply because the two purple values are exactly the same. So had it just been water to air, you would also have seen a 40-degree switch to a 59 degrees as well. Okay, final issue. Let's take a look at that idea of trying to go from something slow to something fast and having too big of an angle and seeing it all bounce back inside. So it's called TIR, or total internal reflection. Just looking at the little simulator again, this is definitely undergoing total internal reflection. None of the light's making it out. If I go with a small angle compared to the normal, well, then I do see some make it out. But as I increase the angle between this light beam and my normal line, I do get to a point where it's like, okay, right there, like that's the edge, that's the end. And when this angle over here on the fast side, which is often air, when that fast side angle hits 90, there's nowhere for it to go. We would actually call the angle over here on the slow side the critical angle. That's when it's like, okay, here it comes. We're right there. We're at the critical angle. And then past the critical angle, nothing but a mirror, nothing but TIR, just reflecting on the inside. So we're going to talk about what happens mathematically when your calculator is trying to warn you that TIR is happening like this, like maybe you've got a really big angle here and TIR happens, or where is this critical angle? What is that last angle on the slow side that gives you a 90 degrees on the fast side? So looking at it from the point of view of cars, what if you were in the mud trying to get out onto the highway, but you had a really big angle compared to the normal, or I guess you could say a small angle compared to the boundary? If that happens, your car might get to the highway and the passenger side tires might get so much traction that it twists the car back into the mud and you end up never getting onto the highway. That's what TIR, total internal reflection, is all about. But again, I think we should take a look and see what that does mathematically on your calculator to warn you that it's happening. Here's a light beam that's traveling through some glass. It's going in this direction and going like this. It gets to this boundary and a portion is making it out right now and a portion is reflecting. That seems to be behaving normally, but once we go too far, then we are going to get this TIR. So this one's great. Incident ray in, a little bit of refracted ray coming out, a little bit of reflected ray, behaving nicely. But if you go too far, then you might end up with this scenario. Nothing but a reflection. Okay, so no refracted ray. This angle is just too big. It's past the critical angle, and 100% gets reflected. So this angle in the little graphic here is about 55 degrees. That's too much. It's past the critical angle for glass. Here it was 40 degrees, and that was fine. Things were working. So what's your calculator going to do to warn you about that? Let's try this story. 75-degree angle on the glass side, going to try to make it out, and I'll tell you right now, this is a lie. It doesn't make it out. It's going to do TIR, total internal reflection, but here's what the calculator will do to warn you. You fire up Snell's law, and you throw the numbers in. On the glass side, I have 1.5, sine of 75, and then 1 for air, and the sine of that angle. Now 1.5 times the sine of 75 is around 1.449. And when I try to unsign that, my calculator goes, whoa, no. And that's actually great. It's warning me. It's telling me, hey, this is not going to happen. You are not going to get a refracted ray coming out. So when we see that on our calculator, you can go, oh, okay, hey, thanks for the info. And you can say, nope, and all of the energy will get reflected back just like a mirror. Okay, with a 75-degree in and a 75-degree out of that little mirror bend. So 100% of the energy comes back at you. Now, the critical angle. that's the moment when everything just starts to get totally reflected. So in a simple sense, it might be like this. You've got a 90-degree angle here on the fast side, which is often air, and then critical angle down here, which in this story looks like it's around 41-ish, 42 degrees. So I'm going to just kind of generally say, yeah, the critical angle is when TIR begins. So the critical angle is the slow side angle when the fast side angle is 90. Maybe we should put that in our notes. Okay, so the critical angle is the angle on the slow side. It's the slow side angle when the fast angle is 90. Often, but not always, the fast side is air. And that's what it is for this picture. So I've got my critical angle happening. I'm going to try to find this angle for water, and then 90 degrees over here for the air side. And I'm just going to let Snell's law do its thing. So 1.33 for the water side, looking for that slow side angle. 1 for the index for air, and then sine of 90, which is also a 1. So nothing but a 1 happening on that side. You divide by the 1.33, and we get this decimal, and then we just unsign it, 49 degrees. So for water, the critical angle is around 49 degrees. For that little photograph I showed you a second ago, it looks like for glass it might be around 41, 42. And that's the moment when TIR is going to begin. Now, if you want to, we can even label this and say, yeah, not only is this the incident angle, this is the critical angle, right? That's the moment when it all starts to happen for sure. I'm just going to try that out with the little simulator, and then that'll be the end of this lesson. So for air and water, we should see around 49. Let's give it a try. So I'm going to put water over here and air. We'll see if we can just, with this little simulator, see what the critical angle looks like. So that would be right around, oh, it's pretty coarse here, right around there. If I take my protractor, does this look like around 49? Yeah, pretty close. 30, 40, 50 is here on the protractor. So yeah, man, as best I can tell with this little simulator, it looks like around 49. And then if we do the one we saw in the photo, that one was glass. Well, that angle was around 42. Okay, looking at the photo, see if that looks like that here. Yeah, pretty close. 30, 40, a little bit, 42, 43. So the critical angle is just the angle on the slow side when the fast side angle has just reached its maximum and it's at 90 degrees. And that's the end of our second lesson.